Hey guys, today we're just going to go over some problems about limits. And as we know, a limit is a y value that a function approaches as it nears some value of x. So let's do an example of a problem that we have done in class, but it's still good to go over it. So let's start with y equals 1 over x minus 1. So as you know, there is a vertical asymptote at x equals 1, and if you draw the graph, it's going to look something like this. And let's make it the limit of this as x approaches 1. Now, the standard procedure for us in our class, but not on the AP test, it would be to plug in 1 for x. But as you see that, if you do that, then you get y equals 1 over 0, and that makes a function undefined. So you have to find values that are close to 1. Or you could follow the protocol that our dear teacher has taught us. So that's going to be number 1, the big lie, which OG has already taught us because, that's when you plug in the 1 into x. However, that doesn't work, so you have to do number 2, algebra. However, if you look at this, you can see there's really not much to do. There's no trig functions, there's no square roots, so there's really not much to do here. So when there's nothing left to do, then what you're going to want to do is graph. And here we have the graph right here. So if you look, for limits, you have to look at the function from both sides, both the positive and the negative side. So let's look at this function. So the limit of f of x, which is this function up here, as x approaches 1 from the positive side. Now, when you do that over here, you can see that as you get closer and closer to 1 from the positive side, your y values go up and up and up and up and up, but they never actually get, or rather your x values never actually get to 1. So what you would write here is just equals positive infinity. And it's the same thing if you do the limit of the same function as x approaches 1 from the negative side. That would be negative infinity, because you can see over here that as you get closer and closer to 1, the y values get really, really big negatively, but the x value never touches 1, so you don't actually know. So it gets larger and larger with no limit. And then following that, you would end up writing, therefore, the limit as x approaches 1 of f of x does not exist. So now let's draw an example where you use only algebra and not a graph. So let's start out with the limit of x squared minus 1 over x minus 1 as x approaches 2. Okay, so there's two ways that you can do this, so let's do the first way. So the big lie is your first step. So you can do the limit as x approaches 2. Now you can't show that you're plugging in the 2, because that would imply that you haven't checked values, because that's the true way to do it, but it's easier to just plug it in, so we're going to do that. So 2 squared is 4 minus 1 is 3, and then 2 minus 1 is 1, so this would end up equaling 3. Now you can also do it this way, so the limit of x approaches 2, and then if you factor that, you could do x plus 1 quantity times the quantity of x minus 1 over the quantity of x minus 1. Cancel these, so you just get the limit as x approaches 2 of x plus 1, and if you plug in the 2, obviously you're also going to get 3. So those are two ways to do it with algebra. Now you could graph it, but there's really no point if you can just plug it in. So that's where you would use the big lie and just the big lie. Okay, so let's look at some complicated ones. So we start off with the limit of the greatest integer function of x as x approaches 1. So first, let's graph this. So we have our little graph here. And we know that there is a closed circle at 0, 0, open circle at 1, 0, and then closed circle at 1, 1, open circle here. So let's label these points. Okay, and as always, you have to look at these from both sides. So if we do the limit of the greatest integer function of x as x approaches 1 from the negative side, we get 0. Because if you approach 1 and you're going this way, here we go, this is 1, 0 here, so as you go this way, you get closer and closer to 0. Or rather, you can see that you remain at 0. But if we approach it from the positive side, and you can see here we go this way, you are moving along y equals 1 instead. So as you get closer and closer to 1 from this direction, your y-coordinate is 1. And so here, because these don't match up, we would say that the limit does not exist. So you would do your 3 dots, and then the limit of the greatest integer function of x as x approaches 1 does not exist. But if we look at the same function, but with a different approaching value, so the limit of the greatest integer function of, or rather as x approaches negative 1/2, the answer changes. Because if you see, if we begin here and look at the positive side, if we come from this direction, and we're approaching x equals negative 1/2, so we're here. So you go this way, then your y value is negative 1. So you would write negative 1. However, if you go from the negative side, so you start here, and you go right, and you go to x equals negative 1, you're still at negative 1. So your answer will also be negative 1. And therefore that limit is negative 1 because they match. So just because it's the same function doesn't mean that that the limit's going to be the same. You have to look at what x approaches before you can write your answer. Okay, now let's look at absolute value. Now there's more complicated problems than this. This is a pretty simple one, but it has the general idea, so we're going to start here and then work our way up. So this reads the limit of the absolute value of h divided by h as h approaches 0. And we know that if we plug in 0 for the big lie, that's step 1, then you get 0 in the denominator, which is undefined, so we can't do that. So we're going to kind of split it up into different parts of algebra. So we know that absolute value, whatever you put within those brackets or lines or whatever, is going to be positive. So it's kind of like a negative positive problem. So what we're going to do here, we're going to split it into 3 different scenarios. So the first one is if the absolute value of h is greater than 0. The second one is if the absolute value of h is less than 0, and if the absolute value of h equals 0. So let's start. So if h is greater than 0, then the limit of the absolute value of h over h as h approaches 0 will simply be h over h. And we know that a factor over the same factor equals 1. So keep that there. And if the absolute value of h is less than 0, then you would do the limit of absolute value of h over h as h approaches 0 equals negative h over h equals negative 1. And then if the absolute value of h equals 0, then it's the limit of the absolute value of h over h approaching 0 equals 0 over h equals 0. Now you can see that none of these are the same. so they don't approach the same value, and therefore, three dots equals therefore, the limit of the absolute value of h over h as h approaches 0 does not exist. Okay, so let's do a little example of where you're going to have to use some strange algebra. So we have the limit of this function as h approaches 0, but you can't big lie because if you do that, then then the function will be undefined. So you have to use weird algebra. So here, I would multiply to rationalize the numerator. So that's going to be multiplied by the conjugate, so plus the square root of x. Same thing. Those are parentheses. X plus h plus the root of x. So the limit x plus h minus x times h times the quantity of x plus h, the square root of x plus h minus, or plus, excuse me, plus the square root of x. Now, this has to be set up like a proof, so you have to show every single step, which, yes, that does mean that you have to write this terrible limit thing over and over again, but it gets easier. So you can see here that the x's cancel out, so you can put h over h times this quantity here. And you can also see here that the h's cancel out, so we're going to cancel those. So the limit as h approaches of this function as h approaches 0. So 1 over x plus h plus x, and this should end around here. So you have this square root right now. So let's try the big lie again. So if you were to plug in 0 for h, then you would get, let's do a little scratch work over here, 1 over the square root of x plus the square root of x, which is 1 over 2 times the square root of x, but you have to rationalize it, so that becomes x, square root of x rather, over 2x. And that's actually going to be your final answer here. But, all of this stuff here, do not show that, because that's technically cheating. And a little word of advice, so whenever you have if it's a trig function or if it's square roots, then always try to rationalize either the numerator or denominator first, because you really don't want to have to plug in values or graph it, so this will be much faster. So if it looks anything like this, then try to use algebra first, after the big lie. Okay, so our last topic is going to be about trig. So we know from the squeeze theorem that the limit of the sine of theta over theta as theta approaches 0 is equal to 1 by the squeeze theorem. So we proved that already, but there's different variations of it. So let's try something that's similar to that. So how about the limit of the sine squared of 2 theta over theta squared as theta approaches 0. Now I'm going to rewrite it for now just so you can see. So let's split it up. So how about the sine of 2 theta times the sine of 2 theta? You'll see where I'm going with this in a second. Times theta times theta. So, yeah, you're going to want to split it, because what you can see here is that you're getting something similar to the squeeze theorem. So we want to make this look like what's up here. So let's go this way. So the limit, and so you're going to have 2 of these. So the limit of the sine of 2 theta over theta multiplied by the limit, and this is really close, I'm sorry, okay, kind of made it, yeah, it's the same thing, these are the same thing, okay, and hopefully you can see here that, we're close to getting sine theta over theta, or some matching dimension of it, but we're not quite there, because instead of sine of 2 theta over theta, we want sine of 2 theta over 2 theta. So we're going to multiply by 2 over 2. And we're going to do that twice, because you have two quantities, and they both have to be normalized to the sine of something over the same something. So that leaves us with 2 times this. So the sine of 2 theta over 2 theta. That's one quantity, times 2 times this same thing over here. Because like these two over here, these match. And so we know that we know that the limit of sine 2 theta over 2 theta as 2 theta approaches 0 is the same in structure as what we have up here. And we know that that's equal to 1. So this part here is also equal to 1. So that just gives us 2 times 1 times 2 times 1. Because remember, this and what's over here are the same, so you just do the same thing. So 2 times 1 times 2 times 1 is equal to 4. And just note that your purpose in any trig function basically is to get your final product, or like one of the pieces of the split trig function to look like what we have from the squeeze theorem. And you know that you can't plug in 0 for theta, because then you would get something undefined. So this problem is a little bit more complicated, but it's the same general principle. So if you'll remember earlier how we split up the quantities, because our goal is to get the sine of, here we want the sine of 3 theta over 3 theta. So let's split it. So this is what you get when you split it, because remember, your goal is to get sine of 3 theta over 3 theta. So we have 2 times where we can do that, because the quantities are squared, and after you're done splitting the squared quantities, you still have a cosine of theta left on the denominator. So you just have the limit of 1 over cosine of theta as theta approaches 0. And so now we have to turn the thetas in the denominators into 3 thetas. So we're going to do that. Sorry about the handwriting. But because basically you want to get the 3 theta on both of those quantities, both this quantity and this quantity. So what happens when you do this is that the 3 in the numerator in this part here, that just moves over. So then you're left so then you get 3 times the limit of, and then this changes too, so 3 theta. As 3 theta approaches 0, because it's going to change to 3 theta. So sine 3 theta over 3 theta. Because now you no longer have theta, you have 3 theta, so then this part changes. And then same thing over here, so 3 times the limit of the sine 3 theta divided by 3 theta as 3 theta approaches 0 times. Now you didn't change this one because, as you can see, there's no need to get it to equal 1, because the cosine of what we have as theta equals 0 is a non-zero. So we just leave that as the limit of 1 over cosine theta as theta approaches 0. And here we can see that these quantities match our squeeze theorem, because it's the sine of something over the same something as that something approaches 0, which equals 1. So we can rewrite this as 3 times 1 times 3 times 1 times, okay, let's look over here, because we have the limit of 1 over cosine theta as theta approaches 0. However, we know that the cosine of 0 is 1, and 1 over 1 is 1, so the limit of 1 is just 1. So this whole quantity here is just equal to 1. So 3 times 1 times 3 times 1 times 1 is equal to 9. And you might end up like multiplying by some weird stuff, but we'll get into that. And here's an example of when you're going to multiply by some weird stuff. So as we know, our goal is to get sine of something theta over that something. So here you're going to multiply the whole quantity by 3 theta over theta divided by 2 theta over theta, and it's over 2 theta. And it's going to like generally follow that model, so just keep that in mind. So when you do that, you are getting the limit as theta approaches 0 for 3 theta over sine 3 theta 3 theta over 2 theta times the sine of 2 theta over 2 theta. Okay, and you don't actually have to write it out like that. I'm just showing you just so you can see where I'm getting stuff. So you're going to split it again. So this becomes the limit of sine 3 theta over 3 theta as 3 theta approaches 0 times the limit of 3 theta as theta approaches 0 all over the limit of the sine of 2 theta over 2 theta as 2 theta approaches 0 times the limit of 2 theta as theta approaches 0. Now it looks big, but there's a couple of like key points here. So here we know that since it's the sine of something theta over something theta as something theta equals 0, Mr. Luna would say whatever, we know that this equals 1 here and that this equals 1 here. So 1 times the limit of 3 theta as theta approaches 0 over 1 times the limit of 2 theta. Sorry, this should be yeah, okay. This should just be theta. Approaches 0. And here we can take out the coefficients. So let's make it 3 over 2 times the limit of theta over theta as theta approaches 0. Now 3 over 2. Now theta over theta is 1. And we know that the limit of any constant is just that constant. So that's going to be times 1 equals 3 over 2. So this thing here turned into this over here. Now I know that it says, sine 3 theta over sine 2 theta, and then it's kind of obviously like the 3 over 2 turns into 3 over 2 over here. But you can't just cross off the sine and the theta. It has to be this. You need this work right here. So just as an overview, whenever you have a limit, your first step is going to be the big lie. So plug in whatever you're approaching into the function, and if it works, then you're great. If it doesn't work, if you get an undefined, then do algebra until you can get it defined, and then do the big lie again. However, if none of that works, then do a graph, and you have to approach the value from the plus side and from the minus side, or from the positive and negative, whatever. It's a little different for absolute values, but we covered that, so if you're confused, then just go back or ask me. And the final way is to plug and chug, basically. So if none of the 4 methods work up top, then you basically just find values that get closer and closer to what x approaches. So if you have, as x approaches 4, then what you're going to do is you're going to plug in values that are very close to 4. So first we can do 3.9 and 3.99 and then 3.999, and then on the other side you do 4.001, 4.01, 4.1. And then you can kind of see, like what number that all of these values zero in on. Now, it could be for any function, but here we just chose 4. It could be 3, it could be 79 billion, but it probably won't be. But yeah, you're rarely going to come to a situation where you have to plug and chug. there might be one on the test, but that's only if you've exhausted all of these options here. So good luck.